belonging to Indonesia. So this is Khurram Shabir, Professor of Mathematics from Government College University, Lahore, Pakistan. First of all, I would like to thank the organizers for inviting me as a main speaker in their international conference on mathematics, the first international conference on mathematics. So the title of the talk is on the Milnor Fibrations for real analytic mappings. First, I would like to give you a little motivation and the background behind this subject, and then I will be defining these tools which we will be using to do the surgery. So this problem is a surgery to remove the singularity from the variety. So this is basically the idea. So we will be doing it geometrically. For example, if you have if there is a tumor in a brain, so whether if the tumor is very less, it is very less in quantity. So here I will be telling you the mathematical way or geometrical concept how to remove that tumor. It's a kind of surgical operation for the singular varieties. So this is the problem we are going to discuss. I mean the Euclidean geometry. We are interested in measuring the angles and distances. For example, if I have a triangle, this triangle, in Euclidean geometry, we are allowed to either move this triangle or to rotate this triangle. So these are the two things we are allowed in the Euclidean geometry. Because here we cannot stretch, stretching is not allowed. So the movement in a way that the angles and the length of the edges stays the same. So this was in classical geometry. Now we move to the projective geometry. So in projective geometry, we are a little bit more flexible. For instance, here the two objects, they are projectively equivalent. If, for example, if you see here, this looks like an ellipse, this picture. But this projection, if you look at the projection, it looks like a circle. So it means these two objects, the circle and the ellipse, they are projectively, they are equivalent. Right? Next. When we move to the topology, we all know this topology is a rubber sheet geometry. Here, the two objects are equivalent if we can move from one object to another object by a continuous transformation. So by continuous deformation, I mean we assume that this is made of, it's a rubber, it's a band, rubber band. So you can move from this picture to this picture without disturbing the continuity, without cutting it. So we start from the square, you can move continuously from the square to the circle, and then the triangle, and then many other pictures. So in this geometry, all these objects are the same. Next. So when we move to the differential topology, in differential topology, this square and the circle, they are the different objects. Why they are different? Because here we are expecting the transformation, but that transformation must be the smooth. Smooth transformation means that this object should be differentiable everywhere. It means you can draw the tangent at every place. But here you can see these 4 points. You cannot draw tangent at these points. So that's why these two objects are different in differential topology. Next we move to the smoothness. So smoothness is something we can check locally. So the smoothest place we know is the Euclidean space. For example, if we talk about the one dimensional, it's a real line. This is the smoothest place we have. If we talk about two dimensions, it's R square, R3, and so on. So these are the smoothest places we have. This leads us to the following object. So this is the object we are going to study. So what is manifold? For instance, if I give you some space, topological space, for instance, if you have a circle, so this circle, if we look at this circle locally, so this locally is nothing but the piece of line. Yes, so it means this piece, is open piece, is homeomorphic to real line. So that means that this object is a manifold of the dimension 1 because locally it is homeomorphic to R1. So that is why this is a manifold of the dimension 1. Similarly, if we move to the higher dimension, if you look at this sphere, in this sphere, if I take a point here, you take a point everywhere. If I take point here, and if I consider the open neighborhood, so this is an open disk. And this disk is locally is homeomorphic to R2. So that means if we move at whole sphere, wherever I move, and if I consider the local neighborhood, that local neighborhood looks like R2. So that means that this sphere is the manifold of dimension 2, right? Similarly, if I consider the torus is the same. If I'm here, if I take a local neighborhood, and if I separate this piece here, this is again homeomorphic to R2. So this means this torus is also a manifold of dimension 2, and this is true for all n. So this is the definition of manifold. As you can see here, a topological space M is an n-dimensional manifold if you take any point on the manifold, the local neighborhood at that point, that should be homeomorphic to Euclidean space of the particular dimension. And then from this dimension, you deduct the dimension of the manifold. Yes. So the next is about the real analytic maps. So real analytic maps, they are the maps between the two manifolds. Once you have manifolds, then there is a map between these two manifolds. For instance, F is a map from Rn to Rk, or you can take it more general from M to N, right? So that map is real analytic if for every point, if you take an open set U here and you take a point x0 from this open neighborhood of x0, then you can always write a power series of this function. So what does this mean to write a power series of the function locally? It means that this function is differentiable and it is infinitely differentiable. The first derivative exists, second, third, and so on. All the derivatives exist. And also, this is one thing. And the second thing is, all the partial derivatives of this function, they exist and they all are continuous. If this happens, then we say that this map is an analytic map. So this means you can write a power series locally at every point. If you can do this, then that function is called analytic functions. And this is of course the picture of analytic function, because the writing a power series locally means it is differentiable, and you can find a tangent bundle everywhere. You can draw a tangent everywhere. It is a kind of smoothest space. This is one of the picture of analytic function. And then is the next concept is a fiber bundle. So fiber bundle, for instance, if I have a space, so this is very well known to all of us, this is a cylinder, yes. So if I project this cylinder under some map over S1, so this is S1 multiplied by some interval, if this is interval, open or closed, whatever. So what do I mean by fiber bundle? So fiber bundle means, for example, if I am here, so what is the inverse image of this point? So it means if this point is some alpha, so what is F inverse of alpha? So F inverse of alpha is this line. So it means wherever I am and at this line, this map will project me here at this point, right? And if I move here, so this is the fiber of this point, and so on. And this happens everywhere. At every point, we have a fiber. Yes? So what if I attach all these fibers here? For instance, if I attach the fiber here, if this is a circle, if I am here, I am attaching the fiber here. And if I move on this circle and attaching all the fibers, so what I will get is this cylinder. So if I can do this, so this means this map is a fiber bundle. So that means locally you can write this space as a product space. If you can write any space in a product space, so that means that is a fiber bundle. It means everything is fine here, right? So this means this definition. So this is very important definition. As you can see here, the fiber bundle is a mathematical structure that look like a collection of fibers, these fibers that are attached smoothly to a point in a base space. This is the base space, and you are attaching all the fibers and moving around this base space. And then what you get is the whole space. So this means the fibration. So roughly speaking, the fiber bundle means if you can write the space locally as a product space, right? There is no singularity, there is nothing unusual there. Next. So here you can see one example is this, the projection of the tube on the circle, and the other example is this Mobius band. Yes, here you can see that Mobius band, for instance, if you have this strip, if I attach this strip without giving any twist, so this is the cylinder, this is the cylinder, but if I give a twist and then attach, then this is the Mobius strip. But if you move along this surface, is a circle, right? So at every point, the fiber is moving along that Mobius strips. So that means there is again no singularity there. So you can write this space as a product of two space. So this is another example of Mobius of the fiber bundle. Next. So now we move to the singularity. So what do I mean by singularity? So we people have read about critical points, yes? So this is somehow the critical points of the space. If we look at the definition, so why we are interested to know the singularity? Here is an explanation. As we are interested in a fibers on a manifold, because we are interested in the fibers of a manifold, yes? So when we assume that when these fibers would be interesting, right? So this is the question. So we are studying the local structures of the fiber. If the fiber is a manifold, for instance, if I am here and the fiber is just a line, so this is a manifold because this line is locally one-dimensional manifold. So that means we have nothing to do. We know the geometry, we know everything about the smooth manifold. Yes, so this is not so interesting if this point is not singular. So such points are called regular points. I will be defining later. So regular point means the fiber is a smooth manifold. Yes. So it means if we can check the fiber of a regular point, if it is smooth, then locally it is a simple space. We have nothing to do. But maybe globally it has some beautiful structure. But what happened if this point is a singular point? In the case of singular point, this fiber is locally very non-trivial in general. Yes, that is why we are interested in the singular points, because here even locally the fiber of that point is highly non-trivial. So here you can see the definition. The function f is a map from manifold M to N, and the point P in M is on M where the function is not submersion. So what does it mean by submersion here? Because this is the map from M to N, and differential of f here means is a Jacobian matrix. If the Jacobian matrix is form of the partial derivatives, so if the Jacobian matrix of this differential has a maximum rank, so maximum rank means the dimension of this space. So then in that case, all the points in the domain are regular. But if the rank of that Jacobian matrix is less than n, in that case only the singular points exist. So here you can see that if the point P on M where the function is not submersion, then that point is called a singular point. Yes? So this was about the singular point. And of course, since f is a map from M to N, and we are taking the point P here, so this point P is singular if this happens, if it is not submersion, if the function f is not submerging at the point P, right? So then if this point P is a singular point here, the image of that point, which is here, is called a singular value. So these two are very important points here. So I will be telling you later when, because these are basically the brain tumors, these singular points. And ultimately, we have to remove these singularity using some surgery. And behind that surgery, there is mathematics. And in that surgery, we will be using all these tools. Next, please. So here is an implicit function theorem. So implicit function theorem means if you have a function and you cannot write the function as in this form globally, but implicit functions tells us if the Jacobian matrix is non-singular, only in that case you can write the function explicitly locally. So this implicit function basically tells us how to write the function implicitly locally at that point. So this is all. Next please. So this is again about the singular point in values. I told you here, if we are finding the point here P, and that is a singular point, the image of that singular point here is singular value. Next, these are the definitions. So here you can see the algebraic varieties, and this is the variety where everything is smooth here. There is no singularity. And here in this algebraic variety you can see this point. This is the singular point. And here this singularity is isolated singularity. Isolated means in the neighborhood of this singularity there is no other such singular point. So it means there is only one tumor there.
Yes.
So it is easy to remove that. Next. Here you can see an example. So how to find the singular values and point. For example, if you look at this example, this is the map from R3 to R2. So this is the map from R3 to R2, and this is defined as f of x, y, z is defined as x comma y times x square plus y square plus xz square. Right? So how to find the singularity here? So if you see that here you can see the Jacobian matrix. The Jacobian matrix means the partial derivative with respect to x for the first coordinate and then the gradient of the second coordinate. Right? If you take the partial derivative with respect to x is 1, with respect to y is 0, with respect to z is 0. And similarly, if you find the derivative with respect to x is this one, with respect to y and with respect to z. So this is your Jacobian matrix. The question is the rank of this matrix. If the rank of this matrix is 2, because here the dimension of this space is 2. If the rank is 2, then there is no singular point. Right? So we will get the singularity only if this part is 0. If this part is 0, then the rank is less than 2. So this part 0 means you take this is 0 and this is 0. If we take this 0, so that means x is 0 and y is 0. If x and y is 0, so that implies it doesn't matter what z is, this equation is satisfied. So that means this 0, 0 and z. So these are our singular points. It doesn't depend on z. So what does this mean? These are all singular points, but this is not isolated singularity. Why? Because if you consider, because this is z-axis, if you are here, 0, 0, 0, if you consider a neighborhood around 0, you will get more singular points. So that means this is non-isolated singularity in this case, right? So what about, so this was our singular points, but what about the singular value? Singular value means the points where this f of x comma y, this function is 0, right? So if we put f of x, y, z equal to 0, so that means this part is 0 and this part is 0. If we substitute this, x is 0 and this is 0, so from here we get y is 0. So that means in this case only 0, 0 is our singular value. But this singular value is here and this is isolated. This singular value is isolated. It means it is possible that you have the points in the domain, the singularity is non-isolated, but under some map the singular values, that is only singular value, only one value, an isolated singularities. So here of course it shows that this has we computed the isolated singular points and the values. Next please. Next important concept is about the transversality. So what is transversality? Transversality means, for instance, if I give you two pictures here, one is this one and another picture is this one. So this is intersection of two submanifolds, right? But this intersection is a tangent. So transversal means if I move a little bit, intersection should not change. But if I perturbate a little bit here, so what we get, if I move a little bit, so intersection is this. So this intersection and this intersection, they are different. This is tangent, but this is not. So it means that such intersection is not transversal. But in this case, if I move a little bit, either I move this piece or either I move this piece, in both cases, it does not matter. It doesn't change the intersection. So this intersection is transversal. So this is the geometrical explanation to check the transversality. Mathematical explanation is in the next slide, please. If you see here, this is the map. So this is the map. F is a map from R to R square, and this map is defined as f of t is t comma t square. So this is the graph of this map, right? And you take a submanifold. This is the submanifold, and this submanifold is this x-axis, which means y is 0. So this is our W, and this is our F, right? So then we compute the differential, and this is the gradient matrix, and this is the gradient matrix at t is equal to 0, this vector. So what happened here? You can see that at this point, if I draw a tangent along this W, it is this one. If I draw a tangent on this submanifold at this point, is the same, right? But these two things are in R2. So you cannot generate the vector space of R2 by using only this vector. You cannot generate. You need at least two independent vectors to generate the vector space here, right? Similarly, here in this case, if you look here in the next, please. In the second example, you have this intersection, and this is point, say, 1, 4, and this is 1, -4. So these 2 points, but here, if I draw a tangent along this surface and this surface, in this case, this is one vector is 1, 0, and the other vector is 1, -4. So these two vectors are tangent vectors locally here. And these two vectors are linearly independent.
Yes.
Since they are linearly independent, so they generate the vector space of R square. So that means that this intersection is transversal. Right? So this is the meaning of transversality, roughly speaking. Next, please. So next is the Milnor set. So Milnor set is those points of a space where you have the singularity. Right? So these Milnor sets are the point where the map and that submanifold, they are not transversal. It means if you don't have transversality, then there is some problem. Transversality ensures the smoothness. If there is no transversality, it means there is some singularity there. So here you can see that. This set is the point where the map and the manifold are not transversal. As you can see here. We know that this is the critical point. Why? Because it's a tangent. It's not the transversal intersection. Right? So this is somehow the general concept as you people have read in calculus. Next, please. Next. Next is about the analytic sets and the semi-analytic sets. So analytic sets is a subset of a real and complex manifold that can be described as a solution sets of a real analytic maps. For example, next please. For example, here you can see that. So this is an example of a real analytic map. Solutions of this equation. Solution of this, what is the solution of this equation? Is a circle. So circle is an example of an analytic or set. And then you can see the hyperbola is the zero set of this analytic equation, because hyperbola is a solution of this equation. So this is again an example of analytic set. Next. And this was about the analytic set. And then is a semi-analytic. What is semi-analytic? Semi-analytic is the generalization of analytic map. In analytic case, you are looking for the solutions of finite number of equations. But here you are looking for a solutions, but here you will have inequalities as well. For example, if you look here in the example, here you can see. So this is the points where this happens and this happens. So what is this part? So this is just a half unit disk, right? So this is an example of semi-analytic map, because here you are looking for the solutions of inequalities, not the solutions of equations. And similarly, this is another example, right? So this is nothing but the inside region of the cone. This is an example of semi-analytic set. Next. And here you have further few examples. The first one is the union of circle and the disk. This is also an example of semi-analytic set. And here you have rectangular region. This is again, because as you can see is inequality. So this is an example of semi-analytic set. And similarly you have this set. Next. So here is another concept, right? So this is about the stratification. So as I told you in the beginning, if you have some brain and there is some tumor, that tumor is a singular point here, right? If that singular point is isolated, it means it's only the one point there. There is only one dot there that is singular. And the idea is to remove that singularity. So how to remove it? To remove it, we cut the spaces. We make the pieces of that space such that every piece is a manifold, is smooth. This is called stratification. You cut the manifold and you remove that singular point. And that singular point surely would come into the closure of that pieces. It comes in the closure of that species. And then once you remove that, is the process of removing that singularity is this stratification. So first I will explain that, and then we will see how to join the parts again. So this stratification means, next. So this is the definition of stratification. If you have a space, any space, so you decompose that space into the stratas, and those stratas of course are disjoint subspaces, and they satisfy the following conditions. So what are those conditions? The first, the strata should be a smooth manifold. Of course we are removing the singularity, so each part should be smooth, yes, independent of singularity. And then the stratas are locally closed. Means each strata is closed in its closure. What does this mean? For example, if I take a real line and if I remove one point from real line, so that means r minus 0. So this is the one of the stratification. What are the stratas here? One strata is this one, M1, and the other strata is this point, M2. So if I take a closure of M1, M2 is there. Yes, closed means it contains all of its limit points. So this is the procedure. And of course, why we are doing this? Because we don't want something that doesn't support the mathematics behind, that doesn't support the analysis behind. That is why we are very much careful to, as you people have seen the layers cake. Those are the stratas, example of stratas. You have seen it's very, there are layers. If you cut the layer, if you take the clear, everything is inside. So this is the way to stratify the manifold. And then of course here is an example. There was a singular point. You consider these stratas. This one in yellow, another one is in this color, and another is in green. And everything is smooth. There is no.
It means stratification is used for dealing the higher dimensions.
Yes, of course, in a higher dimension. Yes. So it means this way we are removing the singular point and dividing the whole space into the disjoint, smooth stratas. Right? Next. So what is next then? Now the question is, once you have cutted the space, how to join it back? So this concept is a regularity concept. Using these regularity conditions, people has of course used the different methods to join that stratas together in a way that when we join those stratas using these regularity conditions, what we get is the removable singularity. There is no singularity there. If we are succeeded to do that, that's all. Yes, as I told you in the beginning, we are doing a surgical operation to remove the singularity and tumor, you can see, right? So this is the Whitney condition. So what is this Whitney condition? If you show me the picture of the next page. So here you can see that this is singularity. Yes. And these are the stratas. Yes. So go back to the definition. So if you look at the definition, we say that the stratas are the disjoint object. This is of course the condition of strata. And if you look here, what is a regularity? If I take a sequence in M1, you take any sequence in strata M1 that converges to a point in that singular strata. You take a point on a singular strata and then you consider a sequence, all the sequence converges to that strata, right? Then the tangent space at all these point of sequences over M1, that tangent space also converges to this Grassmannian bundle. The Grassmannian bundle is, if you are at this point y, at y point there is some tangent bundle there, right? If the sequence of that tangent spaces is converges to that tangent bundle, so that means that if this is true for any pair of stratas, so that means that this stratification satisfies the irregularity conditions, right? So this means these are all to make sure it doesn't, there is nothing unusual. What you are doing is you are trying to check the smoothness basically, because if you are considering a sequence and then you are considering a tangents of the sequence, so that means locally you are checking, is there any singularity there? And this should be true for every stratas and for every sequence. Well, what does this mean? It means we have checked locally everything.
It means connection between two stratas by converging the
Converging
sequences
this
from one
to another, right? So this way it means if we satisfy this, so this means this is the irregularity condition. This is one regularity condition. So what about the next? So there are many regularity conditions. So if you look at this B regularity, it's more or less the same, but what is the difference? The difference here is stratification is the same. You take a sequence xi's in M1, and if you take another sequence in M2, in the first case there was one sequence and one fixed point, but here you are considering the two sequences and the secant lines between these two sequences. For example, if this is x1 and this is y1, so this is the secant line. X1, y2, this. So in this case, initially we were converging through the sequences,
Yes.
but here we are considering the secant lines.
Yes.
So this is the sequence of secant lines converges to that tangent bundle. So here maybe we are more careful, right, to check whether we are going through that straight line and moving it along the stratas to check whether everything is fine, everything is smooth there, right? So this was second condition. Next there was there is a C regularity. So in this case he considered not the lines but the planes. But the planes, right? So here the only difference is instead of secant lines, you are considering the sequence of planes and obeying the same property. Next. So this was all the ingredients I wanted to approach our problems. So these were the tools I was explaining. Yes, to do this surgery. So what is the problem now? So back into 1960, Milnor was a physicist, American physicist. Yes.
5 minutes left for your presentation.
No, I think I have 1 hour and 15 minutes.
Sorry, if you only have
Addressed by Milnor. What is this question? If I take analytic map from some Rn to Rk with a map germ at 0, the map germ means locally, you are looking for locally. So if U is an open neighborhood of 0 and F is a map germ with an only isolated singularities at 0. 0 is the only singularity there. So what is the question? The question is to study the fibers, the topology of fibers, right? So we are interested in to study the topology of fibers. If this point T, if this point here is a regular point, if 0 is regular, so F inverse of 0 is the manifold. So we have nothing to do.
Regular value.
It's simple space, yes? Because in this case it is just a disk. Right? So what happened, but globally it could be interested, but locally it is just a manifold and you are done. But if this point is singular point, then even locally it is highly non-trivial. Next. So this was a very celebrated problem in 1960s when the people were interested to study the differential structures of the manifolds, particularly exotic spheres. Right? So here the Milnor and other people, they prove for very nice results. So I'm going through it quickly. They defined this analytic map. This is holomorphic map. And they study the singularities of these maps. For instance, if you check here, so this is our singular link. So it means this is V is F inverse of 0. This is a singular link, and these are our F inverse of t when t is non-zero. So these are the smooth, there is no singularity there, right? So what he do is, if we take an intersection of this fiber with a sphere S epsilon, where epsilon is a smaller number, so this intersection is transversal. There is a result which tells us that this because for a sufficiently small sphere, this intersection is always transversal, as you can see here. Yes. If this is transversal, so this is nothing but the manifold, and manifold of dimension, in this case 2n minus 1. So this is one of the beautiful way to construct manifolds. You see, this manifold is intersection of fiber with a sphere. So this way you can construct the manifold. This is one of the beautiful way. And if you look at the intersection of this fiber and this is manifold, and if you look at the intersection with this is another manifold. So if we remove this singular fiber, all the other fibers, F inverse of t, where t is non-zero, they all are diffeomorphic. So it means that the complement have the same homotopy type. So this means you have fibration here. The Milnors proved that there is a fibration away from this singularity. So you know the fibration means locally is the product space. And there is a very famous result by Form and Briscoe, which says that every exotic sphere that bounds a parallelizable manifold is diffeomorphic to the link of the singularity coming from the previous from this equation. It means that this polynomial, this singularity, classified all the exotic spheres. All the exotic spheres, they are coming from these form Briscoe singularities. Of course, it varies, it depends on AIs. If you change AIs, you get the different things. But somehow this was a remarkable result by Form and Briscoe, which classify the exotic spheres, right? All the exotic spheres, they are parallelizable. Parallelizable means they are fiber bundles. Right? They are coming from this polynomial. Next. And then of course this was the Milnor result. And in Milnor result, if you see here, this one, this is this tube, this is our n, here, this n. And Milnor proved that if the function f is holomorphic with isolated singularity only at 0, in that case you have a fibration over the tube. Here you have S1 and you have this fibration over this
Disc.
over this punctured disc.
Yes.
Right? And in the second part of the Milnor's theorem was that if you can move this fibration from the tube to the
Singular.
sphere using the integral lines.
Yes.
Right? You use the integral lines to move the point from boundary of tube to the sphere. So this way you get the fibration from the sphere to this S1. Because from the sphere to S1, if you take a point here, you use the line integral to move on the tube. Once you are on the tube, you use F and you are there.
Yes.
So using these two things, you are getting the fibration from sphere to
Circle.
the circle, but of course deleting this link. So this way, and these two fibrations over the tube and over the sphere, they are all equivalent, right? Because why they are equivalent? Because this map from the tube to the sphere, this vector, these line integrals, they are injective maps and they are surjective. Injective means it's, and also the important fact is all these fibers are transversal to this sphere. Transversality is there, one onto is there, so that means this tube and the complement
Projects.
of the tube over this sphere, they are all diffeomorphic. So that is since they are diffeomorphic, they have the same homotopy type. So then you can extend this vibration from tube to sphere, and these two vibrations are equivalent, right? Next. And of course, these are the open problems. The problems here are, I'm going to end this. Problems here are, what are the maps? People are looking for the analytic maps which have the vibration, the one thing. And then of course you are imposing the condition whether these functions are isolated with isolated critical point or isolated critical values. But these two conditions are already very restrictive and very strong conditions. And the second thing is whether is it possible I can project, because in the complex case we can do this this vibration, we can inflate this vibration from tube to sphere only in the case of complex. In the real case you can inflate it, but that would not be coming from this beautiful map, F over F map. This vibration from sphere to circle only by this map, only in the case of complex hypersurfaces. In the case of real, there is the map, but that map doesn't come from this special map, right? So, and these are the results by different authors. They considered this map with isolated singularity, and of course they defined their regularity, and then they are showing that there is Milnor fibration. Then next, this is our result. We generalize the Maria's result in the case of isolated critical value. We extended that result, and of course we have defined our regularity condition here. Next. And then there are some results. One of my students, the Rizwan, he would be going to present tomorrow, and he will be telling you details of these two articles. Next please. Where we link the C regularity, and we use the C regularity and D regularity to prove the Milnor fibrations, both over the tube and over the sphere. Next.
Orthogonal map.
And these are the new results. Next. Next. And then at the end there is a relation between the D and C regularity, and these are the references. And thank you very much.